The penalty function feature in ASAP allows you to replace constrained optimization with a series of less constrained conditions whose solutions ideally converge to the solution of the original constrained problem. To understand penalty functions or to motivate their use before illustrating them with an ASAP example, we turn to a general common example of a penalty function, optimizing the trip of the classic traveling salesman. The famous traveling salesman problem involves optimizing the route of a salesman when visiting several cities in a geographic region. This classic optimization problem was one of the original problems solved by simulated annealing among other techniques. The problem is to optimize or find the shortest path for a salesman to travel between the cities within a limited geographic region to reduce travel costs. Minimum travel costs could be considered the merit function. The added constraint of this problem, and where the penalty function is applicable, is that some cities are separated by a river. The salesman must pay an additional fee to cross the river to visit cities in his sales region. For this salesman, a river crossing would be considered a constraint. That is, he would rather not allow it to occur because of the increased cost. However, river crossings are necessary for his business, so he wants a route that limits river crossings by penalizing those potential routes for excessive river crossings. This is a plot of the various cities that the traveling salesman can travel to. After optimizing, this is the resulting route of the traveling salesman. This same technique can be applied to optical systems, and we will demonstrate this next with an ASAP example. In order to illustrate this process in ASAP, we will look at a very simple problem designed to demonstrate the use of penalty functions while not complicating the objective function. We will design a compound parabolic concentrator, a CPC, to minimize the RMS angular ray deviations out of the concentrator. A CPC is a non-imaging optical system that is normally used in solar collection or concentration applications. The CPC is a parabolic reflector segment rotated about an axis other than its normal axis of symmetry in a way that satisfies the edge ray principle. The edge ray principle forces all rays from the extreme input angle to basically focus at the edge of the output aperture. However, when a CPC is used in reverse, it becomes a luminaire. The example system has a very simple Lambertian-emitting circular disk source at the small end of the CPC. The longer the CPC, the more collimated the light reflected from the CPC walls, so the optimization task is trivial and is meant to be so to illustrate penalty functions. We will minimize the RMS ray deviations by changing the extreme ray angle of the CPC while constraining the length of the CPC to demonstrate the use of the penalty functions. The length of the CPC in our particular example here will be analogous to the river crossings in the traveling salesman example. First, we define our variables. The variable is the CPC entrance or extreme angle as defined in ASAP's Axicon command. We go up to the editor button and choose Optimize Script, and we see immediately that the background color-sensitive editor of ASAP has changed to a black and white editor. This lets us know that we are in the optimization mode inside of ASAP. We select theta as our design variable, and we set its minimum angular departure to 15 degrees and its maximum to 25 degrees. Next, we define our objective function. The objective function in this particular case is the RMS spot size, or RMS ray deviations out of the CPC. On this screen, we will also include the CPC length, so that when the objective function is displayed during the optimization run, we will see the change in the CPC length too. However, note that we will disable this as a term in the objective function or merit function. Next, we will define our objective constraints. The objective constraint in this example is the CPC length. We will set its minimum value to be able to vary between 15 millimeters and its maximum value to vary up to 40 millimeters. Next, we will define our penalty function. The penalty function is defined as 10% of the objective function. The merit function then becomes the sum of the objective and the penalty functions. If the constraint is not violated, then the penalty function contribution to the merit function is 0. If the constraint is violated, the penalty function is 10% of the current objective function or RMS ray deviation, which is added to the objective function. As the optimization forces the CPC length to exceed 40 millimeters, the merit function normally would decrease because of the longer and wider CPC, but actually increases because of the penalty function. The optimization will turn to a CPC length less than 40 millimeters since the merit function will be the smallest around this point. In fact, the function should oscillate as it converges to a minimum. We next set our exit criteria, and we'll set this to be 30 trial solutions. We will choose the optimization method, which in this case is actually chosen for us since it's a problem of one dimension, and then we will start the optimization. As the optimization progresses, we will see a plot of the figure of merit versus the trial solution. We'll also note in the output window the objective function and the CPC length, and we can see that as long as the CPC length is less than the criteria or constraint we have defined, which is 40 millimeters, that constraint will pass. When the CPC length exceeds 40 millimeters, the constraint fails and the penalty function kicks in and adds to the merit function. And what we begin to see is an oscillation of the merit function around a solution corresponding to a total CPC length of less than 40 millimeters. Clearly, the optimization routine has figured out that it cannot exceed 40 millimeters total CPC length, and this is primarily due to the penalty function and the constraint on the CPC length. The penalty function enhancement at ASAP is an important component of ASAP's powerful and broadly applicable optimization capabilities.